Hello friends, in this video we are going to discuss about the non-uniform doping inside semiconductor. So non-uniform doping means the concentration of the impurity atoms will vary along the length of the semiconductor. That means suppose we have a semiconductor bar like this and we are going to dope impurity atoms inside the semiconductor. Now, let us consider that we are doping impurity at high concentration in this region and we are doping low concentration of impurity in the right region. So, we can say that in the this is the region where doping concentration of the impurity is very high, and we can also say that in this region the doping concentration of the impurity is very low. So we can say that in this semiconductor the doping concentration of the impurity is not constant throughout the length of the semiconductor. Suppose this is the length of the semiconductor, this is x equals to 0 and this is the length of the semiconductor. I am denoting the length as x. So we can see that the impurity concentration inside the semiconductor is right now not uniform throughout the length of the semiconductor. So for this case of non-uniform doping, we can say that the concentration of the impurity atoms will vary along the length of the semiconductor, along the length of semiconductor. So now this variation of impurity concentration will be of different type. Likewise, if the impurity concentration profile looks like this, that means in this green region the impurity is very high, in the right region the impurity is very low, and the impurity concentration is varying with respect to x in a linear fashion. So the first variation that we can see is the linear variation of impurity concentration with the length of the semiconductor. Similarly, if the impurity concentration vary like this, so this is the exponential variation. Exponential variation. So we can say that another type of variation of impurity concentration is the exponential variation. There can be many more types, but these two types are in the syllabus object. So the impurity profile, this is called the impurity profile. Impurity profile, these graphs. So this impurity profile can be of two types. One is the linear variation, another one is the exponential variation. And this type of semiconductors where the non-uniform doping takes place is called graded impurity semiconductor. That means if the semiconductor has graded impurity distribution, then they are called non-uniform doped semiconductor. And graded impurity distribution means either they will have linear variation of impurity concentration or they will have exponential variation of impurity concentration. So we can say that if we plot the impurity concentration with the distance or the length of the semiconductor, it will look like this. For that, let us take a semiconductor bar like this. So this is a semiconductor bar. Now this point is x equals to 0, and I am denoting this axis as x, or the length of the semiconductor. Now in the y-axis, I denote this axis as y, and in the y-axis I am giving the value of impurity concentration with respect to x. So this is the impurity concentration Nx, and at this position the Nx value is Nx at x equals to 0, it is 0. So Nx is varying in the y-axis, and in the x-axis the x is varying. Now for linearly graded semiconductor, we can draw the impurity profile like this. It will be a linear variation. So this is the linearly graded semiconductor. Similarly, if we go for the exponentially graded semiconductor, then the impurity profile will look like this. So this is the exponentially graded semiconductor. So in both this case, we can see that the impurity concentration is varying with respect to length. So if we want to name this figure, I can name it as impurity atom concentration profile. So this is impurity atoms concentration profile. Now from this profile we can see that if we say that this Nx is the impurity concentration which is varying with respect to x, and for this case let us assume the impurity is donor, so the impurity will be electron. So for the time being we are assuming that we have doped with donor atoms, so we can say that near the x equals to 0 region the electron concentration will be very high. So at this x equals to 0 region, the electron concentration will be very high. So these are electrons. So these are electrons that we have doped. Now in the right hand side of the semiconductor, here the electron concentration will be very low, that is this one. Now, since in this region, in the left hand side region at x equals to 0, the concentration of the electrons is very high than the concentration of the electrons on the right hand side. So we know that now the electrons will try to diffuse from the higher concentration to the lower concentration. So we can say that electrons will diffuse from the left of the region to the right region. So I can write it as diffusion of electron. So there will be a flow of electrons from the left region to the right region. So these electrons are leaving the left region, that is the higher concentration region. So electron leaves. So when the electron leaving the higher concentration region, it will leave behind positively charged donor ions, because we know that after doping, the electron that will be at the doping atom, suppose this is the doping atom, so there will be an extra electron with this doping atom. Suppose this is a donor atom, so there is an electron, fifth electron will be there. So this is the fourth electron. In this way, there is the fourth electrons, and there will be a fifth electron. So this is the fifth electron which will produce the free electrons. So when these electrons will leave, so these donor atoms will become a positively charged ion, and it is a positively charged donor ions. That's why I have written when electron leaving the higher concentration region, it will leave behind a positively charged donor ions. So we can say when this electron will move due to the diffusion force, then in this positive side, so in this left hand side, there will be a large number of positive ions. So we can draw that there will be large number of positive ions when the electron will move from the higher concentration region to lower concentration region. So we can say that there will be a separation of positively charged ions and negatively charged particles due to this diffusion motion of the electrons. So when the positive charge will be separated from the negative charge in this way, so we can say a electric field will be created from positive charge to negative charge. So we can say right now that this will induce an electric field. This will induce an electric field. So this is the electric field due to this diffusion motion, and the induced electric field force direction will be in the opposite direction to the diffusion motion, and at equilibrium condition the induced electric field prevents any further separation of charges. That means suppose the electrons are diffusing in this direction, so this is the diffusion force. Now, since the electrons are diffusing from the left hand side to right hand side, I am denoting as L and R. So electron is diffusing from the left hand side to the right hand side. So in the left hand side there will be positive donor ions created, and this electron will be moving here. So right now positive charge and the electron is separated by some distance, so a electric field will be created in this direction. Now, due to this electric field, the force due to electric field on the electron will be in the opposite direction of the electric field. So this is the force due to the induced electric field, I induced. And we can see that this force direction is in the opposite direction to the diffusion force. So we can say that the induced electric field force direction will be in the opposite direction to the diffusion process. And an equilibrium condition, the induced electric field separates any further separation of charges. That is, at equilibrium condition, this induced electric field prevents any separation of charges. That means it will oppose the motion of the diffusion forces. So we can see that the electric potential phi has been developed. So we can write that the electric potential will be developed. E induced has been developed, and this induced is opposing the diffusion process. That's what I am telling right now. Now, let us take a semiconductor. That suppose this is an semiconductor. If this is an semiconductor, then, and we have done non-uniform doping here, non-uniform doping. If non-uniform doping is done, then suppose this is the high concentration region and non-uniform doping of electron has been done. For the time being, let us assume that we have doped non-uniform electron. So let us assume that this is the high concentration of electron and this is the low concentration area of the electron. So a diffusion force will be created in this direction. So I am writing it as F diffusion. So when the diffusion of the electron started, then we can say a positive charge, positively donor ions will be left behind in the high concentration region and electrons will be here. So there will be a separation of charges. So if there is a separation of positive and negative charges, so we can say there will be an E induced. This is the E induced. And due to this E induced, the force on the electron will be in the opposite direction, force due to E induced. And this force and F diffusion are in the opposite direction. That's why it is opposing the diffusion. Now, so we can say that this side of the semiconductor, due to the non-uniform doping, will be of positive polarity and this side will be of negative polarity. Now, if we assume that it is a N-type semiconductor because we have doped electrons. So if I want to draw the band diagram of this n-type semiconductor, then it will look like this. In the left hand side we can see it is a negatively polarized, and in the right hand side it is positive polarity due to the non-uniform doping. So the band diagram will look like this. This is the Fermi level. So first we have to draw the conduction band, and the conduction band will look like this. So this is the conduction band EC, and this conduction band you can see it is in the tilted mode, because in the left hand side, that means if it is the left side and it is the right side, then we can see that in the right side it is negatively charged or negative polarity. So if it is negative polarity, then the electrons will have more negative energy, more energy. That's why the EC is in the upper position in the right hand side, and in the right hand side it is a positive polarity. So the electrons in this region, left region, will have low energy. That's why the EC is in the downward direction. Similarly, the EV will be same, because we have to maintain, this is the EV, that is the maximum energy of the valence band, because it will be parallel to the EC, because this gap is nothing but the band gap EG. Band gap cannot be changed, and in the middle position of this band gap there will be the intrinsic Fermi level. So this is the intrinsic Fermi level, and so we can say the Fermi level start. So we can say the Fermi level of this n-type will look like this. So this is the Fermi level of the n-type, and this is the total band diagram of the semiconductor that is uniformly doped with the donor ions, and this is the X direction. So this is all about non-uniform doping case in a semiconductor. Thank you.